The reason the Cybertruck looks like that, those flat panels, those sharp corners, that angular shape everyone either loves or hates, has nothing to do with design. It is because the steel would literally shatter any other way. And that one material decision forced Tesla to reinvent almost every stage of how a truck gets built. Most people see the Cybertruck and think someone made a bold aesthetic choice. What actually happened is far more interesting. An engineer picked a grade of steel so strong, so hard, so fundamentally different from anything used in mass automobile production before, that it broke the rules of conventional manufacturing. And then Tesla had to build an entirely new factory just to handle it. A factory that is now the second largest building by volume on the entire planet. A factory sitting on 2,100 acres along the Colorado River outside of Austin, Texas, that cost roughly $10 billion to construct, employs up to 20,000 people, and doubles as the official global headquarters of one of the most valuable companies in American history. What happens inside that building is unlike anything else in the automotive world. Battery cells manufactured on the same floor where the trucks get assembled. Casting machines so large they are measured in thousands of tons of clamping force. A tunnel underneath a Texas highway styled to look like the truck it was built to deliver. And a steering system pulled straight from the architecture of commercial aircraft. The Cybertruck is not just a truck. It is what happens when a company decides that the way every other manufacturer builds a vehicle is simply not good enough. Let's start at the beginning. Not with the truck, but with the ground it stands on. In July of 2020, Tesla broke ground on what it was calling Gigafactory Texas. The site sat in Travis County, just east of Austin, along the south bank of the Colorado River. The choice was deliberate. Texas had offered a combination of roughly $50 million in state incentives and $68 million in local tax breaks. Land was available at a scale that California simply could not match, and Austin was quietly becoming one of the most significant tech and engineering talent markets in the country. What Tesla planned to build on that land was staggering in scope. The factory footprint would cover 10 million square feet of floor space. To give you a sense of what that means, a standard American football field, including the end zones, covers about 57,600 square feet. Giga Texas is equivalent to roughly 173 football fields, all under one roof. The only building in the world with greater enclosed volume is the Boeing assembly facility in Everett, Washington, where wide-body jets are put together. Tesla built the second largest building on Earth, and they did it in under 2 years. The Cyber Rodeo grand opening on April 7, 2022 was pure spectacle. Lasers, live music, thousands of employees and guests on the factory floor. Elon Musk stood at the center of it and said something that would become the defining statement of what Giga Texas was supposed to be. This is the machine that builds the machine. That phrase is not marketing copy. It describes a manufacturing philosophy. The idea that the factory itself is the product, that designing a world-class vehicle and designing the system that produces it are the same challenge, inseparable. And here is a detail that almost nobody talks about when they cover this story. The factory opened 2 years before it could produce its main product. The Cybertruck was delayed, repeatedly. So from April 2022 until November 2023, Giga Texas was producing Model Y crossovers. 18 months of a factory built for one truck running a completely different vehicle, while the engineers behind the walls kept working to solve the problem that made the Cybertruck the hardest thing Tesla had ever tried to build. That problem had a name: 30X cold-rolled stainless steel. Walk up to a standard production car, any brand, any model, and the body panels you see are made from mild steel or high-strength aluminum alloy. Those materials are chosen because they can be stamped. A stamping press is exactly what it sounds like. A machine that presses a sheet of metal between two dies at extreme force, forming it into a curved, shaped panel in a single stroke. Fenders, hoods, doors. Almost every exterior panel on every vehicle you have ever seen came off a stamping press. The process is fast, repeatable, scalable, and has been the foundation of automobile manufacturing for over a century. 30X cold-rolled stainless steel cannot be stamped, or rather, it can be, but it will destroy the dies when you try. As Musk put it directly, you can't stamp ultra-hard 30X steel because it breaks the stamping press. The grade has a tensile strength of over 600 megapascals. Roughly translated for a practical comparison, mild automotive steel typically sits somewhere between 250 and 350 megapascals. The stainless steel in those Cybertruck panels is nearly twice as hard. When you push a conventional stamping die against it, the forces involved are sufficient to crack the tooling, not bend the metal into the shape you want, but crack the tool doing the shaping. So why use it at all? Because the strength-to-weight properties are genuinely remarkable, because it will not rust, because it does not need paint, which eliminates an entire manufacturing stage and roughly 30% of the cost associated with a traditional paint shop, and because Tesla decided the trade-off was worth it. The solution to the stamping problem is embedded in the design itself. If you cannot curve the panels, you do not curve them. You keep them flat. cut them with precision lasers, and then apply carefully controlled bends using heavy robotic press brakes rather than a forming die. That is why every surface on the Cybertruck is planar. The angularity is not a stylistic statement. It is a direct consequence of working with a material that refuses to cooperate with conventional tooling. But Tesla did not stop there. The engineering team actually developed a proprietary high-speed stainless steel stamping process, a world first. The machine runs at 10 strokes per minute and produces approximately 600 parts per hour. It does not use conventional soft tooling dies. The entire press architecture was redesigned from scratch to handle the material properties of 30x stainless, and that machine exists inside Giga Texas, operating on a production line that no other automaker in the world has built. Now here is something that stops most people cold when they hear it. The largest single source of cost in building any electric vehicle is not the motor. It is not the chassis, it is the battery. And at Giga Texas, Tesla makes the batteries in the same building where it assembles the truck. No other mass-market automaker does this at scale. Most companies source battery cells from an outside supplier, Panasonic, KATL, LG, and those cells are shipped to a separate facility where they are assembled into modules, which are then shipped again to the vehicle assembly plant. Tesla does all of that inside one building. The cells go into the truck a few hundred feet from where the cells were made. That level of vertical integration is not common in any manufacturing industry, let alone automotive. The cells themselves are called 4680s, named for their physical dimensions, 46 millimeters in diameter, 80 millimeters tall. Before the 4680, the standard Tesla cell was a 2170, smaller, with tabs connecting the internal electrode to the external circuit. The 4680 eliminated those tabs entirely. The electrode layers are wound in a way that allows current to flow in and out across the full surface area, rather than funneling through a narrow connection point. The result is a cell that delivers more power, manages heat more efficiently, and costs less to manufacture per kilowatt hour. Though Tesla has been careful to avoid publishing exact cost figures. By June of 2024, Giga Texas had produced more than 50,004,680 cells. At peak daily production, the line was turning out over 126,000 cells every single day. By the fourth quarter of 2024, the production rate was high enough to support more than 2,500 Cybertrucks per week. Those are not finished trucks per week, those are cells. But cell output is the gating factor. If you can produce cells fast enough, you can build trucks fast enough. And Tesla had, after years of stumbling with this chemistry, finally found its stride. The Cybertruck's battery pack holds 123 kilowatt hours of usable energy. Regardless of which variant you choose, that pack sits beneath the floor of the truck in a structural sandwich. The battery acts as part of the vehicle's structural spine, not just a passenger riding along underneath it. Every cell made on that factory floor has a path from the production line to a pack assembly station, and from there directly into a truck frame. No truck leaves, no cell ships out. The loop is closed inside a single building. Now step further back into the factory floor and look at the casting cells. Tesla operates 3 Giga Press machines at Giga Texas. 2 of them exert 9,000 tons of clamping force. The third operates at 6,500 tons. To anchor that number in something physical, 9,000 tons of clamping force means that when those platens close, the machine is pressing the 2 halves of the casting mold together with roughly 18 million pounds of pressure. The machines themselves are the size of small houses. The Italian manufacturer Idra built them. They are, individually, among the largest die casting machines ever constructed. What they cast is the structural foundation of the Cybertruck. The 2 9,000-ton presses each produce the rear megacasting, a single-piece aluminum structural component that forms the entire rear underbody of the vehicle. Everything from behind the cab to the rear axle mounts, in one pour. Before Tesla developed this process, first tested on the Model Y, that same rear structure was assembled from 171 separate stamped and welded individual parts. Engineers would cut blanks, press them in stamping dies, spot weld them together in a long sequence of robotic assembly steps, check the geometry, re-weld, check again. The whole process accumulated tolerances at every joint. Every weld was a potential weak point. Every bolt hole was a place where water could eventually intrude. The Giga Press collapses all of that into a single 80-second pour. Liquid aluminum alloy is forced under pressure into the die. In 80 seconds it solidifies. The press opens. A robot extracts the casting. A quality scan checks the geometry. And that component, that single piece replacing 171, moves on to the next stage of assembly. The 6,500-ton press handles the front megacasting. Together, the 3 machines are producing the structural skeleton of every Cybertruck that rolls out of that factory, front and rear, cast in place with a precision and consistency that welded assemblies simply cannot match. And the weight savings are significant. Fewer parts means less material for fasteners, brackets and overlapping flanges. Less material means less weight. Less weight, in an electric vehicle, means longer range. Everything connects. From the casting cells, the structural components move into the general assembly area. The body side panels, those distinctive flat stainless planes, are laser cut from sheet stock and brought to robotic press brake stations, where the precise angular bends are applied. The tolerance requirements are extremely tight. These panels are unpainted, which means any dimensional error is visible to the naked eye. There is no coating, no filler, no final paint pass to hide a slight misalignment. The stainless either sits flush or it does not. The robots doing the bending operate with positional accuracy measured in fractions of a millimeter. The panels are then bonded and mechanically fastened to the cast aluminum structure. Structural adhesive combined with mechanical fasteners. The same approach used in aerospace manufacturing where dissimilar materials need to be joined without creating corrosion pathways or stress concentrations at weld points. Two materials that do not naturally want to sit next to each other, held together with a process borrowed from the people who build planes. Body assembly is where Giga Texas runs one of its most visible manufacturing sequences. Rows of articulated robots, each one precisely calibrated, move across the growing frame of each truck in coordinated sequences. One robot presenting a panel, another applying adhesive, a third driving fasteners, a fourth doing a final positional check with a laser scanner. The entire sequence for each panel takes place in seconds. Once the body is complete, stainless skin over cast aluminum skeleton, the frame moves into powertrain integration. The Cybertruck ships in two primary configurations. The dual-motor all-wheel drive version produces approximately 690 horsepower and 824 pound-feet of torque. It covers 0 to 60 miles per hour in 4.1 seconds. For a vehicle that weighs well over 6,000 pounds, those numbers are genuinely difficult to contextualize, unless you have been in the driver's seat when someone floors it. The Cyberbeast, the tri-motor variant, pushes that to 845 horsepower, with a 0 to 60 time of 2.6 seconds, and a top speed of 129.9 miles per hour. Those are supercar numbers in a full-size pickup truck platform. Each motor is a permanent magnet AC unit, purpose-built for this platform. The front and rear motors are mounted directly at the axles, not driving through a long drive shaft, running the length of the vehicle. That placement shortens the path between motor and wheel, reduces drivetrain losses, and allows each axle to receive independent torque commands from the vehicle's central computing architecture. The torque vectoring, the ability to send precise amounts of power to individual wheels in real time, is managed through software, and software is at the absolute center of what makes the Cybertruck mechanically different from any production truck sold in the United States today. The steering system has no physical connection between the steering wheel and the front wheels. Read that again, because it matters. On every conventional vehicle, every pickup truck, every sedan, every SUV, there is a steering column, a shaft, a rack and pinion assembly. When you turn the wheel, you are physically moving a rod that physically pushes the front wheels left or right. The whole system is mechanically linked. You can feel the road through it. You can feel resistance. You feel the feedback. The Cybertruck does not have that. What it has instead is steer-by-wire. Sensors detect the angle and speed of the yoke as the driver turns it. Those sensor readings convert into electronic signals, which travel to electric motors mounted directly on the front steering rack. The motors move the rack. No column, no shaft, no mechanical link of any kind. The same signal pathway reaches a second set of motors on the rear steering rack, allowing the rear wheels to actively steer as well. Motor Trend named the steer-by-wire system its Best Tech Award in 2025. The redundancy architecture, dual sensor sets, dual control pathways, the ability for either system to operate independently if the other fails, mirrors how commercial aircraft handle primary flight controls. No single point of failure, no mechanical linkage that can seize or break. At low speeds, the rear wheels turn in the opposite direction to the front. The result is a turning radius dramatically tighter than you would expect from a vehicle this size. At highway speeds, the rear wheels turn in the same direction as the front, a slight crab angle that stabilizes the truck through high-speed lane changes. The driver experiences a truck that handles with a precision simply not possible from conventional four-wheel steering systems, because conventional systems depend on mechanical ratios that cannot be changed on the fly. The steer-by-wire system adjusts its effective ratio continuously, thousands of times per second, based on speed and driving input. The powertrain assembly cells at Giga Texas mount the motors, install the battery pack, and marry the entire drivetrain assembly to the body in a single overhead lift. The body drops down onto the chassis, and the two halves of the truck become one. From that moment, the vehicle is structurally complete. The electrical integration sequence comes next. Wiring harnesses are routed, connectors are seated, and the vehicle's central compute platform comes online for the first time. Tesla has been systematically reducing the number of physical connectors in its vehicles over successive generations, replacing networks of point-to-point wiring with higher bandwidth data buses and centralized compute nodes. The Cybertruck is the most current expression of that architecture. The number of individual electronic control units in a conventional modern vehicle typically runs into the dozens. Tesla consolidates those functions into a much smaller number of high-powered compute nodes communicating over a high-speed network. Fewer connectors, fewer failure points, shorter assembly time, easier over-the-air software updates. After electrical integration, the truck enters quality verification. Every Cybertruck goes through a water test, a sealed chamber where nozzles spray the vehicle from all angles to check for any water intrusion around the panel joints, doors, glass and frunk. Because the body panels are stainless and unpainted, even a hairline gap in the fit is not just a quality problem but a visible one. The tolerance standards for panel alignment on the Cybertruck are among the tightest in the industry. Vehicles are then pulled onto dynamometer cells, rolling road test equipment where each truck is driven under load, the motors spinning against resistance, the control systems verified, the brake performance confirmed, the steer-by-wire calibrated for that specific vehicle's sensor set. And then comes the moment that might be the most distinctive delivery infrastructure in the history of American automotive production. Finished Cybertrucks do not drive out of the factory through a conventional vehicle exit. They enter the Cybertunnel. Tesla commissioned the Boring Company, another Elon Musk enterprise, to construct a tunnel beneath Texas State Highway 130, directly adjacent to the Giga Texas site. The tunnel runs approximately 1,000 feet and connects the end-of-line area of the factory to the delivery staging area on the far side of the highway, where customers receive their trucks. The mouth of the tunnel is clad in stainless steel panels and fitted with an LED light bar across the top that replicates the Cybertruck's own headlight signature. The tunnel entrance is dressed to look like a Cybertruck driving straight into the earth, and the trucks that pass through it do so without a driver. Finished Cybertrucks navigate the tunnel autonomously, operating under their own software guidance through the underground passage and emerging on the delivery side ready for handoff. No other delivery infrastructure in the American automotive industry, possibly anywhere, was designed and styled after the product it exists to deliver. The factory built a tunnel, then dressed the tunnel to look like the truck. Take a second with that. First deliveries to customers happened on November 30, 2023. Production crossed 1,000 trucks per week by April 2024. By May 2024, the rate had climbed to approximately 1,400 units per week, which projects to roughly 75,000 vehicles per year if sustained. Across all of 2024, Tesla delivered approximately 38,965 Cybertrucks, making it the best-selling electric pickup truck in the United States for the year, in a market segment it essentially created. That number deserves context. The Ford F-150 Lightning sold roughly 21,000 units in 2024. The Rivian R1T sold around 17,000. The Chevy Silverado EV was still in limited availability. The Cybertruck, the truck everyone said was too weird, too niche, too much of a provocation to succeed commercially, outsold every electric truck competitor in its first full year of production. Musk acknowledged what it took to reach that point. In May of 2023, well before deliveries began, he said, "This was a tough product to design, and even tougher to build." That was not false modesty. The stainless steel challenge alone would have killed the program at any traditional automaker. The 4,680 cell production ramp took years longer than projected. The casting process required engineering iterations that delayed the Cybertruck's launch by more than 2 years from its original target. And yet the factory that could not build the truck for 18 months is now producing it at a rate that no competitor has matched in the electric pickup segment. Now here's where the story gets genuinely hard to wrap your head around. What Tesla has built in Austin is not finished. In March of 2026, Tesla filed plans for a North Campus expansion at Giga Texas that would make the current facility look like the first chapter of something much larger. The expansion is being described as a joint venture between Tesla, SpaceX, and Elon Musk's AI company xAI, with a focus on semiconductor fabrication, a $20 to $25 billion investment in chip manufacturing infrastructure. If fully built out, the Giga Texas complex could eventually reach 100 million square feet of space. Not 10 million, 100 million. That is not a building. That is closer to a city district, wrapped in one ownership structure. The implications of that expansion stretch well beyond the Cybertruck, a vertically integrated company that makes its own vehicles, its own batteries, its own chips, and its own tunnels, is not operating by the rules of conventional automotive manufacturing. It is operating by the rules of something that does not yet have a name. Step back from the future for a moment and look at what exists right now. A building that took less than 2 years to construct, second largest enclosed volume on the planet. It produces a vehicle from raw material to finished product under a single roof, from the steel that starts as flat sheet, to the cells that start as raw electrode chemistry, to the truck that emerges on the far side of a tunnel that looks like itself. That is not a supply chain, that is a closed loop. The engineering decisions embedded in that building, the 30x stainless process, the 4,680 cell, The Giga Press mega castings, the steer-by-wire architecture, are not individual innovations. They are a single argument, made in metal and software, that the way the industry has always built trucks was not the only way. It was just the way nobody had tried to change. What does steer-by-wire do to the next generation of vehicles when that architecture becomes standard? When software decides exactly how a truck responds to input at any speed, in any condition, and every manufacturer has to either match it or explain why they did not? Drop that in the comments, because that question has a real answer, and it is coming faster than most people think. If you made it this far, drop a comment telling me which part of this factory surprised you most: the megacasting replacing 171 parts, the Cybertunnel, or the steer-by-wire architecture. I am genuinely curious which one hits differently. If you found this useful, share it with someone who still thinks the Cybertruck's design was just an aesthetic gamble, because now you know the real reason those angles exist. And if you are subscribed, stay there, because next week we are going inside a completely different kind of American factory, one that has been running for over 100 years and still builds something that most engineers say should not be possible at the price it sells for. The machine that builds the machine. Austin, Texas, 10 million square feet. And they are just getting started.